Okay, so I'm going to try to do two things at once. Normally, in a regular year, I would have had you do chapter 1, and I had to trim some stuff, so I'm going to try to pull it together in this lesson. And it's not hard, so I don't think you'll have too hard a problem with it. So these are in your notes packets, and when we're talking about an inversion, you maybe did some inverses last year in Algebra 2. So like basically if f of x equals the square root of x and g of x equals x squared, what happens when I drop the square root function inside the square function? So basically what I'm finding g of f of x. That's what I'm trying to find. Well, I hope you're telling me you're thinking, well, you just square root, it's gone, and get x. And that's right. So they are inverse operations. They undo each other, and that's all inverses are. Now, another way to think about this is some of you. I don't know if you went to Newberry. I don't know if you ever ran into Emmy Houseman when Joshua was in first grade. Emmy Houseman had him bring this home. Let's see, how can I delete that? How the heck do I delete that? Oh, right here. Delete. There we go. Emmy Houseman had him come home with these in and out boxes, and maybe you remember that. I don't know. Maybe your other teachers had you do these in and out boxes. So if I drop in, I don't know, let's use the x squared and square root functions again, because those are nice to work with. If I drop in 3, what comes out is 9, isn't it? And then I drop 9 into this, so why do I write square root 2? I should be writing square root x. Because what I'm doing now is I'm going to take the square root of 9 and I get 3. So again, those are inverses, so what happened is whatever I drop in here, I get an output, then that becomes the new input, and that gets some output. And notice this is the same as you dropped in originally. So what I'm trying to get you to see is the old x's become the new y's, and the new, right? The old x's become the new y's, and the old y's are the new x's. So in other words, a function and its inverse swap domain and range. Okay, remember, domain is x, range is y. So if I come down here, and this question here at the bottom says, hey, I've got a function that's one-to-one. Oh, what's a one-to-one function? Oh, we got to talk about this. Well, a one-to-one function is, here, let me come, graphically, a one-to-one function is, well, let's graph x squared. A one-to-one function fails the horizontal line test because what happens, I have two possible x values that give me the same y value, not the same x giving two y's, because that would be the vertical line test, and x squared passes the vertical line test, right? That only crossed the graph once, so that tells me that x is only going to give me one y, versus a circle, right? If I have a circle, that fails the vertical line test because that one x value has two possible y values, right? I could have like 1, 1 and 1, -1, right? So that would fail the vertical line test. So that's not a function; it's just a relation. And then why is the horizontal line test so powerful? Well, horizontal line test tells me if I ask you what's the x value that gives me 4, you're going to tell me, well, it could be 2 or it could be -2. So the square function is not a one-to-one function, which tells me if I find the inverse, and where we're going to go with this is that the inverse is just a reflection around the line y equals x, because the old x becomes the new y, right? If I have this function here, let's graph a couple of points. 0, 0, and this is -1, 1, right? -1, 1, and this is +1, 1. And if I graph 2, 4, and negative 2, 4. If the old x becomes the new y, so 0, 0 is still the same. 1, 1 is still there, right? The old 1, 1, and then I'll graph 4, 2. Let's see, where's 2? Right about there. So I get a square root function, right? You see how it's a reflection? And then if I graph the other side, negative 1, 1, let's see, let's go to a different ink. If this is negative 1, 1, the new point will be 1, negative 1, and 4, negative 2, and that doesn't look very good, but see how there's two possible functions there? So two possible situations, and that fails the vertical line test. So if a function is not one-to-one, its inverse will not be a function. Not that that's not useful, it just kind of limits what we can do with it later on. So one-to-one functions are nice because we can do a lot with them. But I digress a little bit. Well, now that you know what one-to-one is, you could do that easy enough. Here, let me get rid of some of this stuff I've written. Okay, so to answer this question, the old function, the function is one-to-one, so that tells me the inverse is a function. And it says the old function has a domain that x is greater than 2. So remember how I just said the old x becomes the new, the old x becomes the new y, and the old y becomes the new x's. So if I have f inverse of x, the inverse, the domain is the old y value. So x has to be less than 1. And the range becomes the new y values are the old x values. So y is greater than 2. You see the way I swap those around? And that's just the cool thing about it. And you'll see it's really cool what we can do with this. All right, so there's that. Is that all of this page? Nope. Oh, good. I'm glad I'm down here. So then, how do you do something like this? I know this is lousy writing. So this says evaluate f inverse of 3, and they tell me that here's this table. So when I'm given an inverse notation like this, a lot of people can figure it out, but I like to break things down a little bit. So what I think about is, isn't that the same? So equals, let me write this out a little bit better. So that way you can kind of see what I'm doing. That equals the answer. Well, what if I do f of both sides? Won't that f and f inverse cancel out? So f of the answer equals 3. So basically, this says, what is x when y equals 3? Well, when y equals 3 is right there, so what's the answer going to be? 1. Okay. How about this one? This says f inverse of x equals 3. See how it's not the inverse? But we can do the same kind of thing. It says, what's y? Basically, what this is basically asking is, what's y when x equals 3? You see how the way I did f of both sides? So when x equals 3, what's y? 7. Pretty easy, huh? You'll get plenty of practice with this, so if that's a little bit confusing. Well, what about this? We got a graph. Instead of a table, we got a graph. Okay, so I made a mistake and I deleted it, so you'll never know I made that mistake, but here. So now we got a graph, and so this says f inverse of 3, and we're supposed to evaluate that. Well, that equals the answer, right? So just like what we did before up above, let's take the f of both sides. Let's f it. Oh, did I say that? 3 equals f answer. Pretend I didn't say that. We're gonna evaluate it. We're taking the inverse, or we're evaluating each side. So this says f of some answer is 3. Well, isn't that saying what is x when y equals 3? So here's I think is 3. It's kind of hard to read, and I think since they try to do these fairly nice, we think that it's going to be x equals 1. The answer is 1, because when x equals 1, y equals 3. And then we say f inverse of x equals 4. So we'll perform the f function on each side of this equation, which cancels out the inverse. And what's f of 4 is basically what I'm trying to say. So 1, 2, 3, 4, and oh, I don't know. What do you think? Think it's 2, 2.25. With a lousy graph, it's hard to tell. But you see what we're doing is I'm saying here's x is 4. What's y going to be? Okay. So rewriting inverses in terms of the parent function is a great way to evaluate them. Let's see. Is that the last one on page 44? All righty. Now, here, let's before I show you how to do this, let's think about this graphically. So here's an xy axis. This is a linear function with a y-intercept of -5, and it has a slope of 3. So I'm going to go up 1, 2, 3, 4, 5 over 3, and I could graph some more points. Now, so this is 0, -5, and this is 3, 0. Remember how the old x's become the new y's? So for the inverse, we're going to graph 0, 3, and we'll graph -5, 0. So 1, 2, 3, 4, 5. And here's this function. And somewhere they cross up there, don't they? I don't know where they cross. We could figure that out, but that's not for today. And see how if we think about the line y equals x, do you see how it's just reflected around that line? It's very cool. All graphically, you can tell if two functions are inverses because there'll be reflections around that line. Y equals 1x plus 0. Because x equals y. You can kind of see it. X equals y. We're flipping back and forth. The old x becomes the new y. The new old y becomes the new x. So that's the graphical approach. So that's what we're going to do here. We're going to pretend f of x. We're not going to pretend. We're going to rewrite f of x as y. And then we're going to swish x and y. This is where the old x becomes the new y. And now we solve this for y. So I'll add 5 to both sides. And then I'll divide by 3. So the y, the new y, is x plus 3 over 3. We could also write that as 1/3 x plus 1. And we could write that as f inverse of x if we wanted to. And that's how you write an inverse. And then you could graph it and not have to do what I just did with the graph. But it's nice to see it graphically with switching points. All right, so now what are you seeing here? I hope you're seeing f of x equals x minus 3 squared. So I hope you can tell me that that is x squared shifted where? Well, isn't it shifted to the right 3? Then it goes up like this. Now, let's backpedal a few minutes. Is that a one-to-one function? No, it's not, because the horizontal line crosses it twice. So this problem is saying make this function be one-to-one by only saying I'm only going to graph x minus 3 squared when x is greater than 3. Now, you could also say less than 3, and then that would be this graph over here. But I'm kind of prompting you for MyOpen Math. MyOpen Math asks you to do this so it's non-decreasing. Well, remember, a function's increasing when it's going from the left to right, and the y is getting bigger and bigger and bigger. And they don't want it to be technically right at 3. It's not increasing nor decreasing, and just accept that as the goddess of math saying that. And we'll talk about that. In calculus, you'll learn why. Or if we have more time this year, I'll tell you why. But right now, as we go left to right, y is getting bigger. So we've restricted it. We're saying, so the new domain is going to be x is greater than 3. What's the y here? What's the range here? I hope you say that the range is y has to be greater than or equal to 0. Actually, we'll put equal to here for both of those. So that's the old domain and old range. If we find the inverse, won't the hold. I'm going to put that on thought. I'm going to put that on thought. We're not going to remember for the inverse though. Let's think about it while I'm going over it. For the inverse, the old y's become the new x. The old range becomes the new domain. So if we have f of x equals x minus 3 squared, we want to switch x and y, right? So isn't that x equals y minus 3 squared? So now we're going to solve this, which means take the square root. And technically, when we take the square root, we should be plus and minus, but because we restricted this to the positive, so it's always increasing, we don't care about the negative square root. And then, so that leaves me this, and then I'll add 3 to both sides. And that's the inverse. So it said find the inverse, there it is. Now, what does that look like graphically? Well, let's see. It's a square root function that's been shifted up 3, right? And we know square root functions look something like this. 1 over 1, square root of 1 is 1. So we'll go over 4, 1, 2, 3, 4. That's going to be 2. So there's that inverse graphed. Here's that parabola graphed. Do you see how they're reflected around the y equals x line again? So that's pretty cool. And if you think about this, this is 3, 0. This is 0, 3. This is what? 4, 1. This will be 1, 4. See how that's all panning out very nicely? So what's the domain of the blue graph? Don't you see it starts at x equals 0 and goes to infinity? If we take this and make it the new x is greater than or equal to 0. What's the range of this blue graph? Well, the lowest point on it is y equals 3. So the range is y is greater than or equal to 3. Do you see how that is just this? So the old domain became the new range. The old range became the new domain. So that all holds. And then let's see here. Here's where we're getting at. So do you remember how the old x becomes the new y and the old y becomes the new x? Well, if the point 3, 2 is on f of x, that tells me 2, 3 is on the inverse. Or we could say f inverse of 2 has to equal 3. So this is almost the better way to think about it. But this is true. This is true. Okay, let's go to the next slide here. They're starting to get long. Okay. Whoops. Let's see, what was I doing here? So find the inverse on a appropriately restricted domain. So what I was doing here, this looks much better in color, by the way. See how it's just reflected. What I did on Desmos, I took y, let's see, y equals x plus 1 squared minus 2, and then to graph the inverse on Desmos, Desmos is very smart, and I can just do this, and it graphs it without having to solve for without solving for y. All right, so again, restricted domain. Why don't you try this? Let's say the domain is going to be x has to be greater than or equal to -1. That way it's this piece here, right? That way we're only looking at that, and we'll only have to worry about that. We won't have to worry about the negative piece down below it. Okay, so why don't you stop the video, see if you can't find the inverse of that parabola, and then come back and watch it. So I switched x and y, and let me scroll this up a little bit so I have some room. So now I'm going to solve it for y. So x plus 2 equals y plus 1 squared. Then I'm going to take the square root, and x plus 2 equals y plus 1. And then I'll have to subtract 1 to get the y by itself. So square root of x plus 2 minus 1 equals the inverse. And we could let's go look at that graph. It's a square root function that's been shifted to the right 2 and down 1. I could believe that. It's hard to see the scale here because of the way I shrunk it up. But I think looking at this, that looks like -2, so that must be 2. And that must be, I don't know now. But this is the inverse. Don't worry about the graph, folks. I can barely see it anyways. All right, now comes the one that people have a hard time with. I have to find the inverse of this rational function. So let's switch x and y. X equals 2y plus 3 over y minus 2. What's so nasty about this is I got y's, I got two different y's, and I only want to have one y. So here's the trick. I'm going to pretend this is a proportion. I'm going to find my cross products. I don't have to pretend it is a proportion, but we don't always look at it that way at first. So do the cross products, and 1 times 2y plus 3 is just 2y plus 3. We'll get rid of those parentheses by distributing the x through. Okay, let me slide this over here a little bit so I have some room to write. Then I'm going to get the terms with the y's on one side, the terms with the x's on the other. I'm just going to do this. I'm going to say xy minus 2y equals 2x plus 3. That way that 2x turns positive. And then here's the trick. You're going to factor out a y. What happens when you undistribute that y? We only have one y. And then we'll divide both sides by the x minus 2. And lo and behold, there's the inverse. Okay, so you're going to have some of those to do in my open math, and I'm going to ask you that on an exam. Now I've got some radicals. We haven't done too much with radicals, so let's talk about this. Well, one thing, we know if we undo this, we're going to get a squared function. So this domain gets limited to what? This domain, x is less than or equal to what? 8 over 6. If I'm taking x minus 8 is greater than or equal to 0. So add 8, divide by 6. So isn't x going to be greater than or equal to 8 over 6, which is 4 over 3. And this function is shifted to the right 4 over 3 and up 5. So this is the domain. The range was going to be, because square root functions look something like this, right? Right 1 1/3, up 5, and looks something like this. So the range, the lowest number is going to be 5. So y has to be greater than or equal to 5. And so we know the new domain, the domain of our inverse is going to be x has to be greater than or equal to 5. And we'll see that here in a minute. And that keeps it so it's 1 to 1. Let me erase this. Now let's find the inverse. So x equals the square root of 6y minus 8 plus 5. We'll subtract 5. And then we shall square both sides. And I'm not going to bother foiling that out. I'm going to leave it just like that. Then I need to subtract, or I need to add 8. And then I'm going to divide by 6, and there we go. And we certainly are not going to clean that up at all. Okay. I mean, I could, but why? Okay, then, let's see. This one, this is a cube root. So I'm going to switch x and y again. If you want to stop this video and try it yourself, you really should, but because it's the first time we've done this with radicals, I don't know if you want to. I switched x and y. I'm going to subtract 3. I'm going to divide cube root. I'm going to divide by a negative to change my signs. So just so I don't have to worry about it, get it out of the way. Sometimes we'll write that as 3 minus x. And then how do I undo a cube root? I raise everything to the 3rd power. So I could leave this as the inverse. And let's not worry too much about it. I know the old domain, well actually, I can take the cube root of a negative number, so the domain is all reals. The range will be all reals. Same thing here. Why did I write cubed there? Squared there. I should be writing cubed. You probably caught that. You probably thinking, what the heck is he doing? Alrighty, so those are the inverses. Is this the last slide? No, it looks like I got others. I don't know what I gave. Oh, yeah. Okay, so this is the formula. Sounds like chemistry, doesn't it? A concentration. If I add, so this tells me the concentration. Let's see, I start with why the 6? Oh, I know. 60 mLs at 10% solution gives me 6 mLs of acid. And then this is the total amount of liquid. So that's why we start with 6 divided by 60 is 10% acid, right? That's what. I did do this problem before, just so you know. It was yesterday, but. So then they want us to find. So let's think about this before I go too far into this. It might be good to let's put it on hold, because we'll be able to answer that later. So if you add 40 mLs of the 50% solution, what's the resulting concentration? Well, that's just we're looking for the concentration after we add 40 more mLs. So isn't that 6 plus 1/2 times 40? I know you could write that as 0.5, but remember, fractions are your friends. So what's 1/2 of 40? 20. 6 plus 20 is 26 mLs out of 100 mL. So that's a concentration of what? 0.26 or 26%. That was easy enough. How many mLs of the 50% solution would you need to obtain to get a 30% solution? So I know the concentration is 0.3. So isn't that an inverse problem? That's why they're kind of telling us find the inverse. Okay, we can find the inverse. We know how to do that. So x equals 6 plus 1/2 y over 60 plus y. Well, it's a proportion. We'll find the cross products. Equals 6 plus 1/2 y. And then 60x plus xy equals 6 plus 1/2 y. You know, I don't want to have to deal with a fraction. I'm going to multiply everything by 2 and clear it out of there. So 120x plus 2xy equals 12 plus 1/2 times 2 is just 1, right? Now we can solve that for y very, very easily. Let's move. Let's see. So I'm going to move the 2xy to the left, or to the right, I mean. And I'll move the 12 to the left. So y minus 2xy. And then remember how we factor out the y trick to isolate it? So we'll divide that by 1 minus 2x, and that's the inverse. Now remember, in this case, before x was the concentration, and x was the amount of acid, and y is the concentration. Now what we have is, well, let's write this out in words. 120 is the concentration, I'll abbreviate, minus 12 over 1 times 2 minus the concentration. That equals the amount of acid, or the amount of 30% solution, right? Amount of 30% solution, that's what we're adding. So we want to get a 50% solution, was it? No, how much 50% solution you need to add in order to get a 30% solution? So let me see if it'll let me erase that. Oh, it still does, good. So the amount of 50% solution, and we want a 30% solution. So 120 times 0.3 minus 12 over 1 minus 2 times 0.3. Now, some of you are going to say, hey, LeMay, you said use fractions. Fractions are more fun. So, all right, let's do that. I mean, the rest of you can calculate it with a calculator, okay? So 3/10 is, 0.3 is 3/10, right? 120 times 3/10 minus 12 over 1 minus 2 times 3/10. Okay, well, up here, the 10 cancels out that. 12 times 3 is 36. 36 minus 12 is 24. Oh, heck. Can I move this down here? Let's get rid of that. So that's 24 on top. On the bottom, the 2 cancels out the 10 and get a 5. So 1 minus 3/5 is 2/5. And when I take 24 divided by 2/5, isn't that 24 over 1 times 5 over 2? That cancels out and gets 12. 12 times 5 is 60 mLs. And I'm hoping those you guys that did this with the calculator agreed, got 60 mLs. Okay. Last thing here. You know what I'm going to do? Stop this video and clear stuff out. Okay, so this says, remember how the inverse, this is the old concentration? So they're asking me, what value, how much 50% acid can I add so the concentration is 0.6? Well, why did they throw this problem into this section about rational functions, or this chapter about rational functions? Well, that had rational functions in it. Let's step back a minute to what we did during week 7. I'm recording this fall 2020, so that's what we did during week 7 when they were only going to school twice a week. Some of you might remember that. I see a rational function that is both degree 1 on top, degree 1 on the bottom, so that tells me it has a horizontal asymptote. That horizontal asymptote is 0.5 or 1/2. Well, let's leave it as 50%. In this case, I think the decimal is more informative. So that has a concentration of 0.5. So that tells me in the long run, the best I can do is 0.5. So I can never add 50%. So let's think about this in real life. I've got a 10% solution. I'm adding 50% solution. So if I put in an infinite amount of 50% solution, the closest it'll ever get to is 50%. I can never get a 60% solution, right? It just isn't going to happen because I'm not putting in acid that's stronger than 0.6 in order to get there. Okay, that's a cool question, and I hope you understand that. So the rest of this slide, the other slides are just homework exercise and everything that I didn't take off. So that's the video. I hope you took notes and can get those exercises done. I highly recommend that you try these. That's a repeat, but you try these questions and what to do. Okay, so I'm going to stop this video and get it uploaded for you. Ask you this on an exam, and if you're doing this for subsets, I'm going to start throwing these things at you. Honors credit, or start doing or do the dual enrollment class. You're going to have